stuff I didn't want.
I think we recorded the last two only, not the first one, right?
Yeah, there's a reason for that.
Oh, okay.
I was talking scandal. Of course, now I'm freaking glad, because look at all the people that are losing their jobs for, oh, you liked this person's meme 20 years ago, you're fired. What the hell? Yeah, so I'm gonna be Mr. Turtle, and I'm gonna crawl back in my shell. You know, whatever you think, I agree with you. All right, so actually I have some great videos out, so I'm glad to say. So let's go back here, let's go back there, and let's see what we got. So we have started off electrical, and let's see what we got. Let's see, that's pretty helpful. 114. Boy, we did a lot of work last time. Good. Okay, so we started talking about, started talking about electricity. And the only reason we talk about atoms is because the atom's got an electron, and electricity is the flow of electrons. Electron's a charged particle, it's got a negative charge. Since it's a charged particle, that means that we can push it around, pull it around with other charges or with magnetic fields. That's a big deal, because that's what made modern technology happen. Now, I don't know much about the world, but I do know it's going to be more electrical next year than it is this year. And we can assume that most mechanical functions, or should I say, any mechanical function that can be taken over electronically is going to be. I mean, I think we're going to see the end of relays, and we're all just going to go to transistors, you know, the solid state equivalent. Everything that we can, well, look at modern electronic engine controls. Instead of doing all these mechanical valves, everything's run solenoid valves. Everything we can control electronically, we do, because the requirements are just going to get tighter and tighter, and the expectations are going to get higher and higher. And as a result, we're going to see that the only way we can effectively perform these tasks is by introducing or accelerating the use of electronics. Okay, so we talked about the fact that, are you taking pictures, kid? We talked about the fact that we can strip electrons off of atoms, or we can add extra electrons to atoms. And when we do that, the atom gets very angry. This is the best way to explain it. The atom gets very angry, and it wants to get back to where it was, with equal numbers of negative and positive charges, equal numbers of protons and electrons. So that's called an ion. And ionizing atoms is the key to how we get these electrons to move, because we create basically a suction effect on half the atoms. Well, we create a suction effect on the atoms in one location and a pressure effect on the atoms in the other location, and then we provide a path for electrons to flow. These atoms eject electrons, they push the electrons. These atoms pull electrons, and they create a force whereby electrons move. We call that electromotive force. Electro meaning electron, motive meaning motion, and force meaning pressure to push. And we call that voltage. So that's what we're doing basically when we're charging batteries, is we're stripping electrons off atoms in one location and putting them on atoms in another location. Well, these atoms with extra electrons want to get rid of the extra electrons, get back to equal numbers of positive and negative charges. These atoms over here want their electrons back, getting back to equal numbers of positive and negative charges. So all we have to do is create a path between the two, and those electrons will go back home. And then everybody will be happy, because they'll all be in balance. And entropy refers to the fact that everything likes to be at its lowest energy state, just like I prefer laying down to standing up. Or buildings crumble, or mountains crumble to the sea. Okay, so that creates electrical pressure, and that electrical pressure is called EMF, electromotive force, or we call it voltage. Measured in volts, that's capital V, and measured with a voltmeter. Okay, so I showed how we create a battery. We take electrons off of this plate, putting them over on this plate. Now this plate has way more negative charges than positive charges. It becomes effectively a negative plate, just like if I take more black marbles and put them in a jar with an equal number of black and white marbles, it becomes a blacker selection of marbles. And this selection of marbles becomes whiter, having lost all the black marbles. Okay, so now there's forces inside these atoms, since they're charged particles. These atoms want those electrons back. These atoms want to get rid of the extra electrons. So all we have to do is provide a path, which we do. We provide a path, but we make the electrons do work for us to get back home. That's called current flow. The flow is called current, measured in amps, amperes, capital A. So just like back in the olden days, when they snuck people into the country, they used to make them carry cocaine into the country or drugs or whatever. Well, we're going to make our electrons do work to get where they want to go as well. So what happens? As current flows through this light bulb filament, it starts to glow. And it starts to glow in the visual spectrum, the photo spectrum, to where it actually creates light. Creates a bunch of heat too, but it creates light. Okay, so what happens? If eventually enough electrons go back this way without pushing them back onto this plate, eventually these two plates end up being exactly the same. And as a result, there's no more pressure. I mean, these atoms are happy, these atoms are happy. There's no pressure between the two. In order to get pressure between the two, we have to start stripping electrons off of this plate again, putting them on this plate. That creates pressure. Pressure for these to go back, pressure for these to get their electrons. That's called charging the battery. I likened it to digging a hole, and when you took the dart and put it over here, this hole got deeper while this pile got higher. The difference between the two, which is to say the slope, increased. And the greater the slope, the more pressure there was to flow. Just like, taking a hose and pouring water down your driveway is going to create much less flow and have much less force than, say, for instance, Niagara Falls. Niagara Falls goes like this. Your driveway's got a slow slope, or at least mine does. Yours is probably a quarter mile long.
So let me get this straight. The bigger the difference of the electrons, the bigger the flow.
The greater the force is a better way to put it.
Okay, all right.
In fact, you look at lightning. Lightning voltage is so high it's never been measured. We're talking about millions of volts. And when you have force like that, that's crazy. I mean, that'll jump what, 1,500, 2,000 feet? That's long. But the weird part, yeah, that's as far as I want to go on that. When lightning hits people, it doesn't usually kill them, but it leaves weird scars, like it looks like lightning on them. That's trippy. So it's very high voltage but low amperage. Yeah. So if we want to, it's just like think of flow as being a skateboard. The greater the slope, which is to say the greater the difference between this elbow and this elbow, the greater the slope, the more flow, the faster the skateboard's going to go. And depending on the size of the wheels and the size of the rider and stuff like that, yeah, in general, it's going to lead to more flow. If the resistance is the same, yes, it will lead to more flow. Which is why, it's much easier to get killed on 600 volts than it is off at 12. That's why we can good point. That's why you can put your fingers on both sides of the battery and it won't be a problem. Try putting, don't try it, but compare it to putting both fingers on the end of 240 volts. That can kill you.
Yeah.
That can fry your brain. In fact, that, cause, heart stop. Okay. So now a battery for an automotive application, a lead acid battery, the difference between here and here, we can't get it more than 2.1 volts. having a nightmare, and that's unusual because my other dog usually has nightmares. So, or night dogs. The chemistry of lead plates suspended in sulfuric acid, which is a lead acid battery, has a maximum voltage of 2.1 volts. That's the difference between this plate and this plate. Well, 2.1 volts ain't going to do nothing for us. But if we hook 6 of them together in a special way called series, positives and negatives, positives and negatives, positives and negatives. If we hook 6 of those together, 6 times 2.1, we get a 12.6 volt battery. Now we call it a 12 volt battery, but it's not really a 12 volt battery. That's just nominal. That's like me saying I live 7 miles from Montclair High School. I don't really live 7.000 miles. It's just an approximation. We call this the battery we use in cars and trucks and whatnot. We call that a 12 volt battery, but 12 volt is very discharged. When it's fully charged, it's 12.6 to 13.2 volts. We can kind of overcharge it, just like you can kind of put more in a sack of potatoes than 5 pounds. Or just like me trying to fit into a XL shirt 2 years ago. That was a joke. Not really though. But the point I was trying to make was you can kind of overfill stuff sometimes. Probably won't stay that way. Anyways, just to clarify, it's a nominal 12 volt battery. Really, we're looking at 12.6, right? 2.1 times 6. All right, so then we started talking about basic stuff about electrical. We talked about plumbing because it's hard to understand what's going on electrically because it's invisible. So we have to understand it in terms of stuff we do understand, like water flow. Okay, so a plumber comes over. What does a plumber want to know about? Plumber wants to know about pressure, flow, and resistance. Okay, pressure is the force that makes things move. You don't have any water pressure, you won't get any water flow. You won't have any oil pressure, you won't get any oil flow. You won't have any fuel pressure, you won't have any fuel flow. Pressure is the force that makes things move. It's measured in PSI if we're talking about water. Incidentally, Michelle, I looked at like videos from last March or last April, and we did cover electrical. My question to you is, do me a solid and look at what we didn't cover, and I want to start with that first. Yeah, so that we can do it that way, because I think there's stuff that we left uncovered from last semester, from that semester.
Okay.
Yeah. All right, so flow. Flow is measured in gallons per minute. When it comes to water, it's just a matter of how much water is coming out. See, this is how hard is it being pushed. This is how much comes out. Well, the relationship between this and this depends on this. Like if you go on 4th Street, west of Vineyard, you're going to see they're putting in a 10-foot diameter drainage pipe down 4th Street. 10-foot in diameter, that's huge. Why do you use a big pipe? You use a big pipe because you're going to have a lot of flow. It's going to have less resistance, for instance, than say a 2-foot in diameter pipe. Therefore, it will be easier for flow to occur. And after all, we're counting on gravity to get flow out of a drain pipe. So as a result, we have to make it kind of big so that, you know, if the resistance gets too big, the whole thing's just going to back up. That would be terrible, especially if you live in that direction. All right, so pressure is measured in PSI when it comes to water, pounds per square inch here. Flow is measured in gallons per minute. Resistance, well, we don't measure it. But for instance, if you have a clogged pipe, it creates resistance, and all resistance is opposition to flow. So these things are always going to be in opposition, right? The higher the resistance, the less flow you're going to have. The less resistance, the more flow you're going to have. Like when never mind. All right, so electrical pressure is called voltage, and it's measured in volts, which is the big capital V. Current, this is the hard one,
Amps.
is electrical flow, and it's measured in amperes or amps, and that's the big A, capital A. Resistance is measured in ohms, which is the Greek letter omega. And here's the important part. You can't knock anybody over with the output of a garden hose, but you sure can out of a fire hose. Incidentally, King of Staten Island, did I tell you? I think it's a pretty good movie.
Was it?
I've seen it like 5 times. Yeah,
Look it
yeah.
up.
Every once in a while I get lucky. So you can't knock someone over with the output of a garden hose, but you sure can out of a fire hose. Well, what's the difference? The difference is a whole lot more pressure and a whole lot more flow, right? Because now instead of going through a 5/8 hose, you're going through a 4-inch hose. And now instead of 125 PSI or 80 PSI, now you're coming in at 1,000. So it's easy to knock people over with a fire hose. Yeah. In fact, you can kill them pretty easy. So what's the difference? Well, it turns out in electrical, we have a phrase for pressure times flow. Well, electrical pressure is called volts. Electrical flow is called amps. So what do we have that's volts times amps? Well, it turns out Ohm's law is P equals I times E, which if we did it in terms of units would be watts equals amps times volts. So this is what describes to us what's the difference between what comes out of a garden hose and what comes out of a fire hose. And we can see the same thing happening, say, for instance, with lights. I mean, there are some lights, like the little bitty Christmas lights you put on your Christmas tree, that are relatively dim. There's other lights that, searchlights, you could see the bombers coming over in the Battle of Britain. Extraordinarily powerful lights. Remember when they used to have the lights that used to go in the clouds when they'd have premieres and stuff? Yeah, you're probably not old enough.
I don't remember that.
Let me tell you how, they'd have Oscars Cornhusker. That was a joke. Okay, so my point
That rings
was,
a bell.
let's go to the next page before we start reminiscing too much. All right, 3 ways we know work is being done: heat, light, and motion. You got a picture of that, Gabe? Yeah, be sure to take a picture of these pages so that you'll have them close to you. 3 ways we know work is being done. See, actually, Gabe can't see because he's crying too much because he's waited freaking 30 years for someone to teach him this. Quack. 3 ways we know work is being done: heat, light, and motion. And work requires energy. Okay, where do we get the energy? Well, there's all kinds of different energy. There's chemical energy, kinetic energy, potential energy, thermal energy, photo energy, nuclear energy. Yeah. Okay. Well, Newton says energy can't be lost or gained. That says right there, sorry. Energy can't be lost or gained. It can only change forms. Okay. Well, energy can be transformed. See, because for instance, inside the internal combustion engine, we're going to change chemical energy into thermal energy. Mechanical energy into electrical energy is what the charging system does. Energy can be transmitted through conductors and wiring. Energy can be stored, like in batteries. I mean, the big problem we have now is that we can generate a whole bunch of energy with solar and wind, but the problem is we need to store it to when there's no more sun out and there's no more wind. That's a big problem for us now. And energy can be used like in motors, bulbs, and whatnot. Okay. All right. Efficiency refers to output over input. You got a picture of that? Now, here's a battery, and it's powering an electric motor. So it's turning electrical energy. Well, it's actually using chemical energy to turn into electrical energy to turn into mechanical energy. But the problem is, it's also creating a bunch of heat. We don't want a motor to create heat. That's inefficiency, which is to say energy we're paying for, but we're not getting benefit from. All right, well, the heat created by the flow of current is I squared R. I is current, R is resistance. So I squared, that means, if you get twice as much current, you're going to have 4 times as much heat. That's the danger we're in. That's why we've got to watch out for resistance. See, current squared times resistance. All right, so there. Talk about circuit. It's called a circuit, which is to say the path from the positive side of the battery to the negative side of the battery is called a circuit because it looks like a circle, same word. And the 4 parts of every circuit are the power source, which is the way we get the energy. That's the thing that creates or supplies the voltage. Let's put it that way. The conductors, which is the parts that connect all the other parts. The load, which is the reason we have the circuit in the first place, like we have a lighting. We have a motor circuit to provide energy to a motor, or we have a lighting circuit to provide energy to a light. And the controls, which is to say the things that allow flow or don't allow flow or regulate the amount of flow. All right, so here we go. Here's a circuit. Got that pic? This is the symbol for a battery. Positive sign means the positive side of the circuit. Notice this is long, short, long, short. Don't confuse that with the ground symbol, which is long, shorter, 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 upside down triangle. This is a fuse, overcurrent protection device, protects the circuit from too much current. Here's a switch, controls the flow of current to the lamp, so it allows us to turn the lamp on and off. And that's the symbol for a bulb. And this dotted line is used in a direct current circuit, like one that a battery uses. That's the vast majority of circuits on a vehicle. That dotted line is used to denote the ground side or the negative side of the circuit. All right, some basics about wires and wiring. Here's a wire, it's got two parts. It's got the conductor, which is usually made of copper. It's low resistance, so that allows electrons to flow. It provides a path for electrons to flow. This insulation is these days going to be made of plastic, and that has high resistance to the flow of electricity. That keeps the electrons from going anyplace else except down the path that we provide. Now, just like your girl or your kids, it's important that your children go where they're supposed to go, but it's also important that they don't go where they're not supposed to go. And the same thing is true with electrons flowing down this conductor, because having them go any place other than that conductor can be not only inconvenient, but dangerous, extremely dangerous. All right, so then we started talking about Ohm's law, Watt's law, and I introduced to you the concept that, you know, we got to learn the fancy, not the fancy, but the formal way of referring to voltage, current, resistance, and power. And voltage is E. Here's the table. You got that picture, Dave?
Yes.
Yeah, okay. So here's the magic triangle. You put your finger over what you want to see, what you want to learn, and it gives you the formula. E equals I times R, I equals E over R equals E over I. Now, E, electromotive force, it's relatively easy to remember. The only real challenge in this is I. And the reason it's I is because the French word for current or amperage started with, well, current started with an I. People are going to use other words, intensity, stuff like that, but it doesn't make any sense to me, so I leave that alone. I just say, you know what? If I told you you could learn a foreign language, but you only had to learn 4 words, you'd say that's the best foreign language ever. Well, electrical is a skilled trade, so it has its own technical language. Yeah? Where's everybody? This is the worst attendance ever. Anyways, oh, we good friend Rudy.
Yeah.
All right, so E is electromotive force, it's electrical pressure, voltage in volts. I is current, which is electrical flow, or amperage in amperes, which you're never going to hear that, or amps, it's all the same thing. It's the capital A. When you look on your meter, see, because you look on your meter, there's the capital V, there's the omega, and over here is the capital A. So I'm getting you set up so you can know what the meter reads. And R is resistance to flow in ohms. That's the Greek letter omega. P is power in watts. And what we have here is the equivalence, the easy cheater equivalence to these formulas. This is the baby way to do it. A lot of times when they're teaching baby way, they do it this way. I just don't want you to be unfamiliar with this, because this is where you're going to see in textbooks and other formal, you're going to be expected to understand this. All right, E is measured in volts, that's voltage. I is measured in amps, that's current flow, and R is measured in R, yeah, it's resistance. All right, P is, this is wrong. That should be W. Power is measured in watts. I is measured in amps. E is measured in volts. Sorry about that. -5. All right. Then we started doing Ohm's law, Watt's law, and equations. All right, you got that, Gabe? Now, this is a battery, 12 volts DC. The positive shows us the positive side. This is a bulb with 3 ohms of resistance.
With how
Okay.
much?
3 ohms of
Okay.
resistance. So PEIR, you got to set it up in this order in order for my little special trick to work. We know that we are given 12 volts of voltage. We know that we're given 3 ohms of resistance. So this times this equals that, or
36.
this divided by that equals that. So 3 times what equals 12? 4. And we can see that.
Get it wrong.
Go ahead and take a picture of that, Mr. Gabe. Yeah, we got to get going.
Isn't it? It's multiplied down and divide up, or am I doing it wrong?
Multiply up and divide down.
Okay.
Yeah. 2 times 6 is 12. 6 times 12 is 72. 72 divided by 12 is 6. 12 divided by 6 is 2. What's worry?
I had it backwards.
Yeah. Okay, here's more ejemplos. So Gabe, take a picture of that. Sorry, I can't review the whole thing, but like I said, it's in the video. So there you go. And I'm just trying to point out here, you know, why they use 240 volts, because it gives you half as much it gives you half as many amps, which means you can use the wire size. That's the electrician. See what you've been missing? See, now I can put twice as many of these lights on the same service because after all, they're only drawing half as many amps. Yeah, so I put twice as many lights. I can also use half the wire size because wire size is based on ampacity, which is to say the amp capacity, the current carrying capacity of the conductor. All right, here we go. Talking about controls. Here's a fuse. It's an overcurrent protection device. Oh, sorry. Go ahead and get your picture right there. A fuse is an overcurrent protection device. That means it's going to protect the circuit from too much current because current brings along heat, I squared R, that we just talked about 4 pages ago. Now, a fuse is not the only overcurrent protection device. We also have circuit breakers. The difference is a circuit breaker is resettable. I'm sorry, it's down here. Now, over here, I wanted to point out that the starter cable is much bigger than the radio cable. That's because this has to carry 250, 300 amps. This has to carry, I don't know, 2 amps, 3 amps. As a result, ampacity tells us that we have to use a bigger wire size when we want to flow more electrons, just like we have to use a bigger pipe if we want to flow more water. All right, I'm going to take a picture of that. Now, while we're there, I just wanted to point out that solid wire is used in houses and factories and stuff like that. But anytime you've got a high vibration environment, like a motor or like a motor vehicle, you're going to use stranded wire. Stranded wire means there's a bunch of small little conductors instead of one big one. It's because vibration would shake this apart, would shake the terminations off for one thing, the ends. And this remains flexible. So as we see like worn motor mounts or something like that, where there's movement between the frame and the engine, it gives us flexibility so it just doesn't tear itself apart. All right, so here's the old school fuses. You'll notice it says 15A and 32B. That means, oh shoot, you know what? I forgot to draw the most important part. There you go. That's the filament inside. You see it's very thin in there. That's so if we try to push more than 15 amps across that bridge, it's going to melt and open up. That's doing its job. That's what's going to protect the circuit from, you know, melting the wires, for instance, or starting a fire. This is the old school fuse. That's the new style fuse. These are going to be color coded. Also, they have these conductors exposed over here so that we can test them without removing them. All right, so we're caught up. Talking about controls. Let's talk about this. Okay, questions, comments, thoughts on that before I move on?
No.
Go like that. Okay, well, the most basic control that you're likely to see beyond a fuse is this little thing right there, and that's called a switch. Okay, well, what does a switch do? A switch is just like a valve. What does a valve do? Every valve controls flow.
Yeah.
Now, a switch controls the flow of current in a circuit. So what I like to do is I like to think of everything electrical in terms of its equivalent when it comes to water, because we're much more familiar with, a garden hose than we are with a piece of wire. I'll say, okay, so this controls flow. But here's the thing about this. It's only on or off. Sometimes that's what we want. A lot of times it's not. But let's talk about the reality of what's really going on with a switch. So let's draw a circuit. Come in here like that. Remember, folks, draw everything I draw. Do it about the same size as I do. This is absolutely inappropriate for you to try to save money on notebooks. Absolutely inappropriate. Absolutely inappropriate. I cannot mention how inappropriate. For you to save $3 and miss out on this material is a freaking sin. It's a huge mistake. This will make you rich. I mean, this will make you millions of dollars. Would you give that up to save $3 on paper?
No.
That would be foolishness. So let's go like this. And then we'll go over here. And we'll say, okay, here's a bulb, a lamp. And then we'll come over here, and then we have switch like this. Over here, we're going to put a fuse to protect the circuit. Let's say, I don't know, 10 amps. This right here is 12 volts direct current because it's a battery. Okay, so what function is the switch performing? Well, if the switch is down, it's like a drawbridge, right?
Mhm.
If the drawbridge is down, then you can travel. If the drawbridge is up, then you can't. What's the dynamic?
It's interrupting the circuit.
Absolutely. Perfect. For current to flow, there needs to be a continuous path. Uh-oh. Continuous, sorry, path. And this is important because we're going to talk about the phenomenon of continuity, and we're going to talk about continuity testing. And it's important that you understand the role of continuity in electrical understanding. Now, you'll notice that even if whatever electrons we have, whatever force we have in the battery, it can only go this far, because what's being created here is a ton of resistance, a ton of resistance. Why can't we drive to Hawaii? Because there's no path. Okay, well, the same thing is true here. The drawbridge is up. We can't get there. In fact, I have a beautiful drawing. Did you get this?
Mhm.
Yeah, okay. All right, well, up here we have the castle. Going to Gabe's house. Here's the castle. Bunch of flags flying like that. Here's Sancho trying to get to Gabe's house. The window there. Hate to be sorry you have to learn it this way. Anyway, so over here is a road, and here's the road to Gabe's castle. Over here is a road like this, but there's a cliff right here, and there's a drawbridge, but the drawbridge is up. And this is the drawbridge that would take you across the mountain to Gabe's castle. Let me do this like this. Yeah, it's a drawbridge. Goes like that. You know how bridges look. There you go. The drawbridge is up. Maybe if you've been to Long Beach, right? The bridge goes like this. You can't have any flow. You only have flow when there's a continuous path. All right, well, here's Sancho. He's standing here wondering what the hell to do because you can't get across. Very frustrating.
That's what invented pole vaulting.
Yeah, that's why they invented pole vaulting. Ramp vaulting. See, because as long as the drawbridge is up, there's too much standing in the way of him being able to get across the valley. Resistance is too high. Why can't I drive 100 miles an hour between here and Bakersfield without using the freeway? Because the resistance is too high. Why can't I just drive to Hawaii? Because the resistance is too high. Now, if we had a path, I mean, you look at what the Florida Keys, I mean, they created a path. So now you can get between all those different islands quickly and easily. But in this ejemplo, the resistance is too high. In fact, we would say that there was infinite resistance because it might as well be infinite because we can't even measure it. I mean, I can't jump 6,000 miles or 3,000 miles or however far it is to Hawaii. I can't jump that far, so it might as well be, 10 million miles. I still can't make it. Okay. So let's go back. You got that?
Mm-hmm.
Oh, shoot. Yeah, there you go. So let's go back. So what is the switch doing? When the switch is open, which is what we call that an open circuit. Resistance
Hi.
is so high, we might as well call it infinite. Infinite means finite means count, in means can't. So infinite means you can't, it's so high you can't count it. And since the resistance is so high, basically we've created a dam that's completely blocked the river. No flow at all. Okay, well, when the switch
Closes.
allows contact between one side and the other, that's called closed. And it's called a closed circuit. And of course, when we close circuits, we can have flow. And the resistance is low. In fact, it shouldn't be any higher than a piece of wire of the same length. Sorry. So when there's low resistance, we get flow, as long as we got voltage here. As long as the total circuit resistance is low enough, we'll have flow. In fact, in a 12-volt circuit, what determines the amount of current flow is the amount of resistance in the circuit. That's an important point to bring up. In a 120-volt circuit, what determines the amount of current is the amount of resistance. In a 240-volt circuit, what determines the amount of current is the amount of resistance. Yeah, less resistance, we're going to have more flow. Like, for instance, let's say I'm putting in a panel and I take my wrench and I rest it between the 240-volt lugs. I'm going to get crazy amounts of current flow, right? Because the resistance is so low. Yeah. Now, you look at this thing right here, 120 volts. Why are these things so far apart? That's to make the resistance high enough to where we don't get current flow between those two. Okay, now go to 240 volts. Now you're going to see that these two things are spaced further apart. Why? Because you got twice as much pressure, so now you have to keep them further apart. Yeah?
Okay.
Yeah? So now we have to have twice as much resistance to offer the same protection. Catch that again? Thought I didn't know, but I did. What? All right. So the problem with the switch is it's on and off. But we also have this. And it's called a variable resistor. like a volume knob on a radio, or maybe it says low, medium, high on the fan motor going to your air conditioner. And what the symbol looks like is this. It looks like a resistor, which is just a regular resistor. So I'm going to redraw the resistor, but this time I'm going to put this arrow like that going through it. And that's called a variable resistor. Now, what does the variable resistor do? Well, it can turn off flow entirely, usually, or it can give us maximum flow and everything in between. So we would say that this was analog and a switch was just digital, ones and zeros, ons and off. This can go on, off, in any speed, like the volume knob on a guitar or something like that.
Or a dimmer switch?
Sure, absolutely, yeah, yeah. So that's different types of controls. Now, are there also things like photo cells, stuff like that? Sure, sure, but that's a type of switch. You know, so the different things we can hook up to a switch and the different type of switches we have. Yeah, but the basic types of controls are going to be either switches, fuses, or, well, overcurrent devices, switches, or variable resistors. You believe that, Chuck? Sounds familiar. Okay. So that's my discussion of controls for now. Now, just
The variable resistor, is that also, have you ever heard of a VFD? A variable frequency drive?
that's different. Yeah, that's different. That's like pulse width modulation. That's like how we control fuel and fuel injectors. We'll get to that later because it's kind of a sophisticated
Right.
kind of a sophisticated application.
Yeah.
Other than to just let me say, the point of the variable frequency drive is that it keeps us at the correct voltage, because motors are very inefficient when you get the wrong voltage going to them. So basically what the variable frequency drive is doing and what pulse width modulation are both doing is it's giving the load full voltage, just not as often. Let me just put it this way, just as a hint. If I have DC voltage, here's my volts on the vertical, and here's time. If I close the switch going to my starter motor, well, I have 0 volts, and then all of a sudden I have 12 volts, and I've got power all through here. This is 12 volts. As long as I have the starter switch on, closed, there's going to be full power going to that starter switch. Well, what we want to do with variable frequency drives and what we want to do with pulse width modulation is we still have to give it full voltage, but now what we're going to do is we're not going to give it to it all the time. As a result, it's going to give us the ability to vary the speed of that motor, for instance, most commonly that motor or that solenoid. Now, what is frequency? Well, it's going to be alternating current. We know that much. That's positive voltage, negative voltage. Here's a frequency like this. That's a pretty fast frequency. Here's a slow frequency like this. Okay. Well, power is only being applied underneath the curve. In fact, this is why they invented calculus, is so you could calculate the area underneath the curve. That describes when power is being applied. Well, this is the reason why they have 3-phase power as opposed to single-phase power, because you say, oh, look at all that power being applied. Well, that's true, but the problem is you need to look at all the time the power isn't being applied, which is this. That's time power could be applied, but it's not. That's the big problem with single phase power and why you can't really get big power out of motors. This is the reason why there's a 3-phase generator inside the alternator of a car instead of a single phase. Because look at all this space. And look, the voltage is going to 0 here and here. So what we're going to do with a variable frequency drive is we're going to vary how long, this is called a wavelength, we're going to vary how long it is. And the more of these we can cram in a smaller space, the more this space is going to be filled up with area under the curve. Therefore, the more energy it's going to get. 3 ways we know work is being done: heat, light, and motion, right? So the more energy we can cram into a certain amount of space, the faster the motor is going to turn. And if we slow down the frequency and spread it out like this, the motor is actually going to slow down. But it's not going to beat the motor up because the motor is still getting full voltage. It's just not getting full voltage all the time. That makes sense?
Mhm.
Yeah. So I can go any percent from 0% to 100% effectively. Same thing's true with pulse width modulation. I think we talked about that in this class, but just in case we didn't, it's the same thing with a fuel injector. You know, you can't give the fuel injector 6 volts. It won't work right, and it'll burn up because it'll get really hot. So we have to give the fuel injector 12 volts. But what we do is we vary the amount of time that that injector is held open, which is called pulse width or duty cycle, and it's measured in milliseconds. So if we want the solenoid to spray, if we want the fuel injector to spray more fuel, we're going to give it power for a greater percentage of any given, time, second, 100 millisecond block, whatever. The longer we keep it open, the longer it's going to, the more fuel it's going to spray. Lots of stuff is pulse width modulated now. In fact, alternators are usually pulse width modulated now. Pulse width modulation and variable frequency is used when we have to provide full voltage, but we want to be able to control the speed. Now, old school variable resistors, here's the thing. If you look at how a variable resistor works, it works by cutting down the voltage that goes to the load. You can't do that with a motor, you'll burn it up. You can't do it with LEDs, they won't work. That's why LEDs have to be run on pulse width modulation or variable frequency. They need to have full voltage. They just don't have it on all the time. So variable resistor is going to cut down the voltage. We didn't do that in this class, but if I have 6 ohms of resistance here and 6 ohms in the bulb, that bulb's only getting 6 volts. Now a bulb will put up with it. An incandescent bulb will put up with it. But there's a lot of loads like LEDs, like transistors, like solenoids, like transformers, like motors. They won't put up with half voltage. You'll burn them up. You'll chew them up. Especially an expensive motor like an industrial motor, you can't do that. No, you can't do that. So that's how they control the speed without using a variable resistor, which would just, you can't, you'd chew it up. Now, a silly motor like a blower motor for a fan, yeah, you could use a variable resistor on it, but that variable resistor is going to get hot. We don't want that. This is a smarter way to do it. It's a higher tech way to do it. It's a more expensive way to do it, but it's a way more efficient way to do it because now we're not just heating up this variable resistor half as much as we are the bulb. We're not putting half the energy into this variable resistor, which would make it very warm. Yeah. Okay. So I didn't want to get too far down that road, but it does have a lot of application now because, like I said, that's how we're using the PCM to control the alternator on modern vehicles, is pulse width modulation. Which means on a lot of scan tools, we can go in there and we can control the alternator with the scan tool, which is groovy. That's how they found the problem on my Z06. Incidentally, Chuck, it took 10 months. Yeah, 10 months it took to show up. Yeah. 10 months. So that's how long personalized license plates take now from DMV. I mean, from AAA. All right, so that's talking about controls. Now, we talked about conductors. Pretty happy with the job we did there. I would like to talk about electromagnetism just because Because I've got a great video for that, an outstanding video for that. But let me make sure that's where we want to go. Yeah, I think it is. Ah, that's it, buddy. All right, control. Yeah, I think that's good. All right. Because, okay, so I have videos from a year ago, like the first videos I made in this class. Cover a lot of this material in case something's not clear. But what I want to do is I want to finish the lesson for the people who were here a year ago that we got most of the way through electrical, but we didn't finish it. So I kind of want to pursue that. What I want to do is I want to cover electrician fundamentals enough to where we can go into real applications, ignition systems, fuel systems, stuff like that, charging systems, batteries, starters, stuff like that. So let's talk about electromagnetism. Electromagnetism refers to the relationship between electricity and magnetism. I saw the best video, and not only that, but oh, happy day. The little brown truck came for me today. Now, of course, I can't get the box open. Well, that would help. Maybe open a half. That's nice. Use a K-bar to open up the plastic box. Got all these little compasses because I got all excited because I watched this video. So I got all these little compasses. So
Cute.
yeah, you would think they'd all be pointing in the same direction, right?
Hopefully.
Yeah. Electromagnetism refers to the relationship between electricity and magnetism. Is there a relationship? Yeah, but don't tell Mrs. Magnetism. That was a joke. The point I was trying to make was there's a relationship between electricity and magnetism. Two aspects of it. Number one aspect is passing current. I got too excited. Through a conductor creates a magnetic field.
Oh, yeah.
Now, this is all about three-phase motor controllers, dude. This is the key to making money on this. Creates a magnetic field. It's also how motors work. And solenoids and relays and all kinds of three-phase motor controller is just a three-phase relay, basically. Okay, passing current through a conductor creates a magnetic field. Okay, what do you remember about magnets? Well, we'll talk about that in a second. How strong? How strong is that magnetic field that gets created by the flow of current? Remember, current is the flow of electrons. How strong? Well, it depends on three things. Number one is the proximity of the parts. Proximidad in Spanish means nearness. And there's limits to how close we can get stuff because as stuff gets hot, it expands and we can't have the things touching each other. Now, due to Maxwell's field equations, magnetism drops off very quickly as you get further away. As the power of the cube instead of the power of the square. It's one of the highest factors in all of physics. So as a result, you get too far away from a magnet, it has no effect on it has no effect on you at all. I mean, you can sense it from a satellite from space, but it's not going to move anything for you. All right, number one, the proximity of the parts. Number two, how much current? The more current, the greater the magnetic field. Because remember, electrons are charged particles, negatively charged particles. So as charges go past us, that creates a force called magnetism. You know, the funny thing was, you know who that was discovered by? It was discovered by, what's it, Henry or Maxwell? Either one of them, they were lecturing at Oxford, and they were going to demonstrate for their students that there was no relationship between electricity and magnetism. So the poor jackass had a compass, and he set it down next to a wire, and he was practicing his demonstration for the students to prove that there was no relationship between electricity and magnetism. And he freaking energizes the wire, and guess what the compass does? And that's how he discovered the electromagnetism. It was either Henry or Maxwell, I can't remember, but whichever one it was. They laughed and laughed. That's a good discovery though. I'll bet your colleagues buy you lunch.
Real quick, real
What?
quick, Mr. Clips. When we try to find the the underground lines that come into a certain building,
Right?
my boss, what he does is he gets witch sticks. He gets 2 copper wires, and he folds them, and basically he holds them lightly, and they'll slowly come to, when they feel the current. Explain that. How does that work?
It sounds like nonsense to me. That they used to
Oh,
find
it works. I've seen it all the time. It works.
well, the flow of current would tend. Well, I mean, it works just like the needle on a compass.
Right. Oh, okay. So that's what I'm guessing right now.
But current has to be flowing through it.
Right.
They had this thing called dowsing, Dowsing. Look it up, and that's how they used to find water, underground rivers and stuff like that. But they didn't know whether half of it was just being a charlatan or half of it, being how to understand geology. I would hope that your boss isn't digging without a blueprint, in which case he should already know where the conduits are.
Right.
In which case I'd have lots of fun showing Gabe my mad skills at, I don't know, but either answer could be correct. What I'm going to show you is I'm going to show you a video pretty quick, and you're going to see the violent reaction of a compass when you pass current through a conductor. It's freaking awesome to see. I love this video. In fact, there's a couple of videos these guys do that are freaking amazing that you should definitely patronize, even if you don't pay them. All right. Oh, incidentally, Scott Brown did a new video, came out 4 days ago, and he's got a 360-degree camera, which I thought was bitching. The video quality he did was freaking awesome. It's a demonstration on picoscope. I got to show you that. Not right now though. How much current? And the third thing is the number of coil windings. You know what I need to do? I need to make a pilgrimage to Connie and Dick's, and I need to crawl there on my hands and knees and beg him to show me his mad skills, because he's got skills for days. I'm so amazed by Scott Brown. I just am. In every aspect, he's a better man than me, except I can probably wreck my life faster than he can. Right? I can have a rank 2 lives. Okay, so Michelle, where do we stand on general public and the English beat?
Can you repeat that?
I like the English beat a lot better.
Yeah, go ahead. I'm sorry, Anna.
What is number 3 say? Number of what?
Number of
Windings?
coil windings.
Sorry, I just read it. Okay, thank you.
Perfect. Yeah, I just scrawled it incorrectly. Because what we're going to do is, when current flows through a conductor, 100-foot piece of wire, it creates a magnetic field, but that magnetic field is dispersed over 100 feet. So what we're going to do is we're going to take that 100 feet of wire and we're going to wrap it, say around, well, in this video, they're going to wrap it around a pen body, this, and then we're going to go like that. So now as current flow, that's called a coil. And these things right here are called windings or turns. What's your favorite Joe Jackson song? Not too much? Okay. I Confess, or
I Confess is a good song.
save it for later?
Those are both good.
I confess too.
Yeah,
Style Council?
they're both good.
Um,
You like the specials?
Oh, Message to You, Rudy. Yeah, I used to play that for Rudy like every class period. Nah, I'm too old to ska now. I have to go to the ska retirement home. Okay, so this is a coil, and all it means is I've taken a long piece of wire and I've wrapped it really tight around something. Usually, I mean, if I want to make it really intense and efficient, I'll wrap it around the iron core. All right. These wraps are called either windings or turns. You're going to see them referred to both times. And a coil localizes and intensifies magnetic field created by the flow of current. Now, localize, that means it takes something that was all spread out and puts it in a very small area. Intensify means it takes a force that was all spread out and crams it into a very small area, which makes it much, much stronger. Okay. So all this is, like I said, is a conductor that was really long and it's smaller now. I want to make sure you know what that looks like. So let's go here. New share, basic, ZX bus, double Dutch. Oh, that's a relay, so that ain't it. Come on now.
Oof.
I've got a lot of those. Golly, you got plenty of those. Coil windings. There we go. Coil windings. All right, well, those are really big, thick ones because that's for an electric motor. You see that? Those are big, thick ones because that's for an electric motor. Now, this looks like bare wire, but it isn't. It's just coated with a clear enamel, so it doesn't short internally. But it looks like bare wire, and it's easy to make that mistake. So I'm going to come here. More commonly, at least in automotive, you're going to see windings that look like this. Now, you ever seen those, Gabe? Those are solenoid valves. See, very small wire. And the reason we use small wires so we can get a whole bunch of windings. See, number 3 is the number of windings. That's the Achilles heel of a coil too. Any electromagnetic device, anything that has a coil, always suspect an open in the windings because they make the wire super small so that they can get a whole bunch of windings in a small space. Problem is, the ampacity of that conductor is very low. So these things, they tend to get hot and then they open up. When they open up, there's no more current flow. Resistance is too high. Well, that worked out well. And since the resistance is too high for current flow, there's no electromagnetic field. These are all valves being controlled by solenoids, which is a pitching picture. I like it. So as you can see, there's all kinds of different coils, and you can admire that at your leisure. Yeah, look at that. Yeah, look at the size of that. Big old heavy stuff. Yeah. You know what you want to do, Gabe? When you take out a old thing that looks like that, first thing you're gonna go down to a recycler and say, you know what, this is made of pure copper, pay me. Like arc welders are like that on the inside. So I wanted to show you, where is that old fella? Of course I didn't. Why would I save it? That would be too intelligent. Not that one. Nope. Okay, so let's go to YouTube. Scott Brown Auto, right there. Okay. Come on now. Scott Brown Auto, you got it. I don't know why it doesn't automatically go to him, but it doesn't. Now it's making me nervous. Is he there? Oh, won't he help me? Oh, that's it.
Because there's a lot of Scott Browns.
Yeah, but automotive? Rather.
I know, I had a hard time finding them too at first.
Okay, so I guess we go diagnostic just to. Plus, he has a diagnostic network T-shirt, which I need to get one. CS track. What the hell? Diagnostic. Okay, where's this new one? Well, here's his channel right there. That's the Scott Brown I'm talking about. You want to get your car fixed, right? He's the one. Now, here's the interesting thing about this. This just came out 6 days ago. Incidentally, R. Kelly just came out with a new album too. But look, look. What the hell?
Oh, that's crazy.
Isn't it?
That's crazy.
Okay, that's not the worst part. Let's go over here. Okay, let's go over here. Okay, so he's using the Pico because he's a Pico endorser and trainer. All right, check this out. About right there. Here's his big TV screen. He's showing you fuel pump wavelength. All right, I got the wrong video. I got too excited. So it's not this one. Go back here. This one. This pissed me off.
Do a quick check here and check the
Pissed me off because it's so much better than what I do.
50 millivolts.
Watch.
So it's seeing all kinds of noise.
Check it out. What the hell is that?
We have to configure what
Somehow
code
he-
we're looking at here.
With some editor or something, somehow he got the picoscope screen to just like show up like it's hanging in space. I don't know what the hell. Scott Brown.
So in this case, I need one ground.
But he's got the Diagnostic Network t-shirt, which is freaking Scott Brown, right? I mean, Scott Brown's got to be top 5 technicians in the freaking country. And he's like 2 blocks away. And yeah, he does videos like that just to shame me, right? You know, just to shame me. Yeah.
Is he your hero? Real
He
quick.
actually is. Yeah, he actually is. He's who I could have been if my character wasn't so deformed. Seriously.
You didn't turn out so bad.
Yeah, I know.
Yeah, lucky. Yeah, I mean, I had a lot of people praying for me.
I'm sure.
I got lucky.
The congregation.
Yeah, all these churches burning down. They're so. There's this great war in the heavens over my.
No, they're still praying for me, so don't feel bad.
Right.
Speak for all of us.
Yeah. Well. So, anyways, a coil localizes and intensifies the magnetic field, and here's what we need to know about magnets, because I know we got 3 minutes, so let's get after this. Just a review of 4th grade science. We got a bar magnet here, a north and a south, and it comes out with, magnetic lines of force, also called flux lines, that go like this. This is how fast you can draw it after you do it all day long for like 8 different classes. Doesn't matter, it doesn't have to be perfect, but these are called flux lines or magnetic lines of force. And this is going to be important later. I think we're going to make very good progress on electromagnetism tonight. So let's do that. Now, magnets are polarized. What does that mean? That means there's a north and a south, a positive and a negative, a red and a black, 1 and a 0, up and a down. They're polarized. Just like direct current, right? If you look at the top of the battery, you've got red and black. And they're opposites. Well, these are opposites too. Now, the flow of current through a conductor, if you're using DC, the electrons are all going in the same direction. That gives a magnetic field direction as well, polarity as well. And that's an important thing to understand, because what we're going to do is we're going to take a steel rod and we're going to put it in the middle of this coil. And when we apply current to that coil, that steel rod is going to move. And the direction it moves is going to depend on whether this is the positive or that's the negative. That's called a solenoid. That's the next thing we are going to study. So let me go ahead and draw it. And then we'll be done. Take a break. Got a steel rod. Why? Because it contains iron. And if we want a magnet to work, it only works on stuff that contains iron. Cobalt too, but mostly stuff that contains iron. Steel is iron plus carbon. So steel is a common material used in this industry. All we're going to do is we're going to come over here. We're going to come around here, go like this, go like this, go like this. I don't know why we didn't get any new students. I think that's strange. I'll tell you one reason probably is because people think of this as a shop class, and people have had such universally bad experience with distance learning that they figure they're just going to sit things out until we go back to school. Well, who says we ever will?
I know.
Frankly.
Yeah.
And I don't think you can afford to take a year off, really. And this is the hard part to understand of this industry. I mean, I can show you how to do a brake job all day long. But this is the hard part to understand. This is the stuff we usually don't have the opportunity to teach. Okay, so I'm going to put battery positive, which is abbreviated B plus here. And I'm going to put battery negative here, I guess you could call it, or you could just use the ground symbol like that. When I get current flow, it's going to create a magnetic field. And this steel rod is going to go this way or this way, depending on which one of these is positive, which one of these is negative. If I want it to go the other direction, like a door lock, door solenoid, all I have to do is reverse the polarity. Same like a window motor. If I put the positive and negative this way on the window motor, the window rolls down. If I flip the orientation, the window rolls up. Because the magnetic field that gets created is going to have polarity. Therefore, it's going to give direction. So this is called a solenoid. And I have a wonderful, wonderful, insanely great video to show you at 7:45. So don't be late. And I know that's cutting the break kind of short, but we overwent on review. And anyway,
All right, we'll be back.
I'm feeling good. So I'll see you at 7:45. Thanks.
Okay. I'm gonna have to scoot over a little, baby. Thanks, Kitty. Come on. Hey, Chuck. Oh, you're not Chuck. Sorry. How you doing?
Good.
I'm doing good. How about you?
Good. Yeah, I got my car problem resolved.
What was it?
It was, I don't know, because I just cleared the code and it never came back on.
All right, you're tough.
Yeah.
Go up a hill. Go up a hill and floor it and see if it comes back. I'll bet you it will.
Really?
Yeah.
Yeah, I was going up a hill when it happened.
Write a letter to Governor Newsom. Tell him we need to open up the schools. He'll listen to you.
And your $25 to get help the petition to recall
That's it. All right, it's 7:45. I'm going. All right, I got the best video ever. You guys are gonna love it. That one too. Not that one. This one. All right, check it. Great, insanely great video, and it's gonna animate a bunch of the stuff that I've been trying to explain. So let's do this.
Hey there guys, Paul here from engineeringmindset.com. In this video, we're going to be looking more into solenoids and how they work. We're going to look at permanent magnets and how to see their magnetic field. We're going to create an electromagnet from a wire. We're going to be looking at some real-world solenoids and also cut one open using some power tools. And finally, we're going to learn how to build our own basic solenoid. If you are working with solenoid valves, you're going to want to download the magnetic tool app from Dan Voss, who have kindly sponsored this video. The app makes it easy to test that your solenoid valve is working properly and works with both AC and DC versions.
I got to tell you, that's kind of interesting. I'm wondering what that is.
You can download it for free for Android and iPhone using the link in the video description below. So we'll start off by taking a look at a standard bar magnet. This is a permanent magnet. You've probably seen these type before. They have their ends marked. One end will be N for the North Pole, and the other end will be S for the South Pole. We can use its magnetic field to move other objects. If we imagine this iron now as a piston in a valve, then we can see that the magnet can be used to move the piston. The problem with this type of magnet is that the magnetic field can't easily or practically be turned off. So in this case, the nail will stay attached to the magnet until we physically put it off. If we place two of these magnets together, we will see that the likewise polar ends will repel each other, but the opposite polar ends will be attracted to each other. If I then place a compass near the magnet, we see that as I move the compass along the perimeter of the magnet, the compass is being affected by its magnetic field, and the compass face will rotate to align with the opposite polar end of the magnet. You'll see it also follows the magnetic field lines. Remember, opposites attract. We can see these magnetic lines if we place the bar magnet down on a sheet of white card, then we sprinkle some iron filings over the top. The iron filings are aligning with the magnetic field lines to create this pattern. These lines always form closed loops and they run from the north to the south. As I mentioned, the problem with permanent magnets is that they are always on and they can't easily or very practically be turned off or controlled. However, we can control an electromagnetic field, and we can generate that with some standard wire. Let's have a look. If we take the standard earthing wire and strip away the outer insulation, we find some copper wires inside. I'm just going to remove this with a sharp knife. Once it's removed, I'll just peel off one of the smaller wires inside. If I place a compass near the copper wire, we see that it has no effect on the compass.
Because there's no current flow yet.
However, if I now connect a power source to each end of the wire, we see that as soon as I pass a current through the wire, current creates an electromagnetic field, and this will change the direction of the compass, just like we saw with the magnet.
But did you see how slow the compass moved? Wait about 20 seconds. I'll show you something really interesting.
The electromagnetic field is operating in a circular pattern around the wire. If I place some compasses around the wire
Check this
and
out.
pass a current through it, you see that they all point to form a circle.
That's cool.
If If I reverse the direction of the current, then the compasses will point in the opposite direction. If we now take the wire and wrap it into a coil, we can intensify the magnetic field. I'll just wrap this around a screwdriver and then compact it until it looks something like this. Now, if I connect a power supply to the coil and pass a current through it,
See how
we
much
see that the
faster it
compass
moves?
will be affected, and it now points at the end of the coil, just like it did with the permanent magnet. When I move the compass around the perimeter of the coil, the compass will rotate to align with the magnetic field lines. If I reverse the current, we see that the magnetic poles will also reverse. When current flows through a wire, it creates a circular magnetic field around the wire, as we saw a moment ago. But when we wrap the wire into a coil, each wire still produces a magnetic field, except the field lines will merge together and form a larger, stronger magnetic field. We can tell which end the north and south pole will be for a solenoid coil by using the right hand grip rule. This says that if we grip our hand into a fist around the solenoid and we point our thumb in the direction of conventional current flow, that's from positive to negative. It actually flows from negative to positive, but don't worry about that for now. But if we point our thumb in the direction of conventional current flow, then the thumb points to the north end and the current will be flowing in the direction of your fingers. So if we have current flowing in this coil from positive to negative, so from left to right, then the current is flowing through the coil towards us, and the north pole will be on the rightmost end. We can check that because the compass will face the opposite direction. Remember, opposites attract. So one compass points north for the coil's south pole, and the other points south for the coil's north pole. If we then reverse the power supply, so the current is flowing conventionally from positive to negative, so from right to left, we simply flip our right hand over. The current is now flowing away from us in the coil, and our thumb points in the direction of north. Our compass points north to the coil's south pole, and the other points south to the coil's north pole. If we now look at this real-world solenoid valve, we see on the bottom there's a metal valve body, and on the top is the solenoid within the blue box. So
Okay.
let's cut this one open and see what's inside the solenoid.
All a solenoid valve is a valve that's controlled by a solenoid. That makes it so we can control it electrically, which is groovy. Now, what does a valve do? Every valve does the same thing. It controls flow. What a solenoid valve allows us to do is to control things electrically instead of, doing this thing with the valve. Yeah, so look,
I'll just place this one into the bench bias, and then I'll use the angle grinder to cut it open. I'll make one cut along the front side, and then I'll rotate it and cut down the other side. There's a few sparks coming out because we're cutting through metal on the inside. And there we go. This section has been cut out. If we look inside, we can see it's a pretty basic design with no moving parts. It looks like there's a solid copper ring inside, but that's just from the cutting blade. If we poke at the coil region, we will see it's actually a whole load of small copper wires all tightly packed together.
now, why are they so small? So that we can get more and more winding. That's the Achilles heel of every electromagnetic device. That's coils, solenoids, transformers, solenoid valves, motors, relays, and generators. The Achilles heel is that the conductor is made small so we can get more windings. Problem with small conductors is they got low ampacity. These things overheat, and when they overheat, the copper melts, opens up. Now we got infinite resistance. We got no current flow. There's no magnetic field being created, and that thing dies. Always the number one thing to suspect when you've got some kind of electromagnetic device.
With a little nudge, they will all fall out. Here's a much smaller real-world example without the protective casing. It's essentially the same, just a much smaller design for a different application.
See, it's got a return spring on it. So after we stop the flow of current, the plunger is going to return to its original at-rest position.
If I connect this to a power supply, we can see that the piston can be pulled in by the electromagnetic field as soon as current starts to flow through the coil. If I cut the power, then the spring will force the piston back to its original position. I can remove the insulation tape to show that it's just a coil. If I then reassemble the solenoid and connect it to a power supply, we see that the piston is moved by the magnetic field and the spring. So now that we know how one works, let's make a very simple one ourselves. I'm just going to use this pen as the core body for the solenoid. I'll just cut this down so it's shorter in length. I'm going to use an angle grinder to cut this for no real reason other than I'm just being lazy and I like using power tools. Now I'm going to melt the ends slightly. I'm going to melt them with a lighter, and I thought I'd just show you this clip of a lighter from my new slow motion camera. This is filmed at one.
Okay, I wanted to show you something that I just noticed the last time I showed this after showing this like 6 times. In the background, you're going to see the lights flickering. What that light flicker is 60 cycle alternating current. And you're going to see that the voltage goes up, then it goes to 0, then it goes down, then it goes to 0. So it turns off. It has 0 voltage and 0 current flow 120 times a second. With the slow motion camera, you can see the power go out. Watch.
1,000 frames
See in
per
the
second,
background,
which is about 20 times
the light
slower.
flickering? That's what it is.
So I'll just melt the ends with a naked flame and then press the ends against a solid surface to spread them out.
I like this video so
I'm
much.
doing this because I want the ends to protrude slightly, which will make the coils easier to wrap. Now that I've melted and shaped the ends, I just need to drill through the excess in the center to allow the piston to oscillate. I'll also just file it down so it's nice and smooth and the piston doesn't catch on the edges. For the piston, I'm just going to use the iron nail. Now I need to wrap the coil. I'm going to use some 26 gauge or 0.4 millimeter enameled wire, which I bought online.
Now, you probably assume that that's bare wire, but it's not. It's wire that's coated with an enamel, which creates an insulation. That's what keeps it from just having a ton of internal shorts. It took me about 30 years to figure that out. Just so you know.
Leave some links down below for where to get that. So you simply want to wrap the copper wire as tight as possible from one end to the other. When we do that, we should end up with something like this. Then we need to wrap it a few more times in opposite directions to make it stronger. 3 or 4 wraps is probably fine. I didn't count the number of turns for this one as I'm just making a quick example for you. Once it's fully wrapped, we can just cut the wire and free it from the drum. Then we want to just use some sandpaper to remove the enamel, which will give us a better electrical connection. So if I place my iron nail concentrically within the coil, but not fully within, we see that the nail piston is pulled inwards by the electromagnetic field of current passage through it. If we were to place a spring at the end, it would return to the original position.
And if we were to reverse the red and the black, it would go the opposite direction.
If we place the piston fully within the coil and then apply a current, the magnetic field will move the piston. And we could use this to provide a pushing force. Again, if there was a spring on the far end, then it could be returned to its original position. I just want to remind you to download the magnetic tool.
Okay. Engineering Mindset has some great videos. How solenoid valves work. That's a great one. You know, it's actually a great one is they have one on how alternators work, and it actually has the animations of 3-phase, which is freaking cool. And what it does is it's stuff that's really very hard to explain, and it's hard to show on paper. But if they've already done the animations, let's use them. You know.
So that's the same way contactors work, right?
Yeah, a contactor is a relay. Yeah, absolutely. See, the problem is with the electrician industry is it's got its own specialized language too. So it calls things 3-phase motor controllers or contactors. They're all relays. So if you understand how a relay works, then it's the exact same thing. Yeah. Yep. Good. You get it. Good. I didn't turn off the recording during the break, so I hope you didn't plan any insurrections or anything. Or if you did, I'll come back later and I'll be able to see if I'm willing to join up or not, willing to support your cause. Okay, so yeah, that's a solenoid. Okay, so how can we make a solenoid stronger? Because, you know, a fuel injector is a solenoid valve. Incidentally, I came up with a great way of drawing solenoid valves. I don't want to overload it. I came up with a great way of drawing solenoid valves. All it is a valve with a solenoid on the end to activate it. Every valve controls flow. The solenoid is just going to be what controls the valve as opposed to us coming out here by hand. You know, the fuel injector is happening, so, you know, 3,000 times a minute, 6,000 times a minute. That's 10 times a second, 100 times a second. Yeah, we couldn't do that by hand, but the computer can. We're seeing solenoid valves take over every valve in the car. Why? Because, well, even the thermostat, we're electronic thermostats now. Why? Because that enables us to use the powertrain control module or the engine control module, whatever, to operate all of these valves, which means we're going to get it happen at the perfect time in the perfect amount for the perfect duration. Yeah, which is way better. Now, it's going to make stuff way more electrical, and you're going to see a whole lot of people that turn their back on that electrical because, after all, they don't understand electrical and they don't have what it takes to sit down and actually study it, be taught it. But we can see this ain't that hard. This ain't that hard. Why have I been freaking out about this all this time? This ain't that hard, you know? Now it's going to get easier for you. The more you study it, the more videos you watch, whatever. Anyway, I just strongly suggest his video on how alternators work. It's kind of involved how alternators work, and it takes a while to teach how alternators work. If I could get you to watch that video, we could shave probably an hour. That would give me an hour to teach other stuff. Now, I didn't want to give you this video before I started teaching this because I think this is the background you need for it. And I think that video was such a strong video, such a strong video. I don't know if you thought so, but I thought it was an insanely strong video and just perfect for what we were trying to accomplish here. How can I make this solenoid stronger? Well, what can I do to make the magnetic field stronger? Well, you know, I can't get the parts too much closer together because the flow of current is going to make everything expand, right? Heat makes everything expand. So I can't get stuff too much closer together. So what are my options? I can increase the amount of current, or I can increase the number of windings. Increasing the number of windings is going to take up a lot of space unless I use very small wire, in which case I won't be able to use much current. Using a lot of current is going to require me to increase the gauge of the wire, which means I won't be able to have as many windings. So that's why you see as an electric motor gets more powerful, what happens to the size of it? Gets bigger, right? Because we need more space for these windings. And that's also why they get heavier too. That's a lot of copper. In fact, I had a friend about 30 years ago said, you know how I choose stereos? I pick it up. I figure the heavier it is, the more copper there is in the transformer, the better quality the stereo is going to be. And I said, that makes so much sense. You know? All right, so that's a solenoid. Now, let me blow my good friend Gabe's mind. Now, why would we want a stronger solenoid? Because the solenoid that kicks the pinion gear out into contact with the ring gear to make the starter motor turn the engine has to be a much stronger solenoid than the fuel injector. And as you can imagine, it pulls, 12 times as many amps. More current tells us it's got to have bigger conductor. Yeah. So what we're doing is we're understanding this stuff on a fundamental level so that we can understand, well, why is the starter relay bigger than the headlight relay? Relays or relay is what I say. Look, okay, so I got a coil like this. Write what I write, draw what I draw, the same size and the same position on the paper that I do, because so what I got a coil right here, and then I've got a switch right here. And when I see that little dash line, and this is all in one box. Gabe, I told you your friend should be here.
I told him, but he's at a party right now instead. He wants to party. He doesn't want to learn. So I told him, well, you know what? I ain't waiting for you.
Enjoy being broke. Yeah. Okay. So what happens is when current passes through this coil, it creates a magnetic field that's going to suck this switch contact down. Okay. So let's look at the rest of the circuit. Over here is B plus coming in this way. Over here is a motor going to ground. Now on AC, it's a little bit different, but not really, not a lot. Over here is a ground as well. And over here is B plus, which is battery positive. going to a switch, and going here. So what's going to happen? Well, if this switch closes, this motor is going to start to turn. So if this switch closes, current will flow through this coil, creating a magnetic field, right? I've got a path from positive plate to the negative plate. Current will flow. There's 12 volts between these 2 points when this switch is closed. That's going to suck the switch closed. Current will flow. That means that if I close this switch, this motor is going to run. And you say, well, you know, what's the big deal about that? I mean, couldn't you just run it like this? Well, yeah, you could, but there's a problem with that. Just use a switch instead of this fancy thing here. Well, yeah, you could, but the problem is, if this thing is drawing 250 amps, this switch is going to have to be rated for 250 amps. That's a big switch. That's a bigger switch than supplies electricity to your house. That's like a two-hander, clunk.
Mhm.
We don't want to do that. We want to have something that the computer can control. So we use this device, which is called a relay. It's going to be called a contactor, going to be called a motor controller. All it is something that allows us to control a big current using a little current. That means we can use computers to control it. We can use PLC, programmable logic control, to control huge amounts of current using relays. And you're going to see relays all over the car. I don't know how much longer they're going to be there, but since they're cheap and simple and everybody knows how to work them, they're all over the car. There's a starter relay, there's a fuel pump relay, there's cooling fan relays, there's air conditioning clutch relays, there's headlight relays. Any situation where you find a high current load, well, shoot. Yeah, I get so excited I want to protest.
Mr. Oakcliffe, the starter relay is also a way of jump starting a vehicle, isn't it? If you get like a screwdriver and you,
Sure. Oh, yeah, like on a Ford? Yeah,
yeah.
yeah. In fact, I think I'll show you one of those. This right here is the door computer for a C5 Corvette. And you can see that it's got relay.
Oh, yeah.
Yeah. And this is what goes bad on these. Incidentally, Chuck, if we wanted to be smart, we would buy these things when they're bad and just replace those relays, and it all of a sudden turns into a very high value part because they don't make these anymore. And if you got a new one, they're like $600, and that's a very
I have a reball machine.
what?
A reball machine. You never heard of that?
Uh-uh.
That takes off surface mount chips on the motherboards.
Oh, that's cool.
Yeah. I used to
Yeah.
use that when I used to repair Xbox and PlayStations.
Uh-huh.
Yeah, so that's a real expensive machine. But if that was a surface mount chip, we can take it off.
Yeah, because that's what's been blocking me besides laziness. Yeah, you can get these 4 relays for like $16. And if we were to rebuild these boards, I could
A lot of
5
times,
to 10 years.
a lot of times those on the bottom of the board, when you try to heat it up, the circuit with the soldering gun is that solder so hard that by the time you put enough heat on there, you burn up the board. It lifts the
Yeah.
contact.
Right.
So I use a reball machine to preheat it, and then you hit it with the solder gun, and then the solder lifts out.
Right. Yeah. All right. We should talk. Why not? Got to prepare for the Mad Max scenarios. Quack. Got to fix all everybody's window relays. But I'll bet you that is probably a common problem with every GM from that era, which means, you know, it's a niche industry, but we could teach like 5 and 6 year olds to do it since they're staying home anyway. That was a joke, Gabe. That was a joke. Everyone's like, oh, we are now recording. Report of child slavery sent. That was a joke. Okay, so this is called a relay. A relay uses a small current to control a larger one. See, I can control this 200 amp circuit with what, half an amp, if that. Why is that important? Because if you've got 250 amps in this circuit, if you want the computer to control the starter, you're going to have to run 250 amps through the computer, which would cook everything.
Right.
Also, the starter switch is on your ignition switch, right? Got a very small wire going to that, probably a number 18 wire. Since that, telling you that there's not much current flowing through it. Okay, this is probably a double aught welding cable, double aught wire to handle 250 amps. Now, if we just used a switch, if the starter switch was a switch in a circuit this simple, you'd have to have a battery cable coming up to the switch and a battery cable going back down, because it would have to run 250 amps through the switch. We don't want that. So how do we get away with using such a small wire going to the starter switch? All it's doing is activating this relay. See, we can use milliamps to control hundreds of amps using a relay. And that's what we do with motor controllers. That's what we do with contactors as well. That's what it is. Yeah. And since it's the same thing, since they're all members of the relay family, we know the Achilles heel, and where they all go bad is this freaking coil. It gets too hot and then it opens up. When it opens up, resistance goes infinite. As a result, there's no current flow. No current flow, no magnetic field. This switch is not going to activate. Now, let me show you some stuff. You got that? Let me show you some stuff on, come on, little thing, you go. Let me show you some stuff to make sure that you understand what it looks like. On a car, you're usually going to have what's called ice cube relays, named after the inventor, I think. Oh, there you go. Oh, that's the one you're talking about, right, Gabe?
Yeah.
The starter relay for a Ford. Yeah. There's an ice cube relay right there. And as you can see, if we were to rotate this diagram here 90 degrees clockwise, it looks just like our drawing of a relay, right? This is the schematic of a relay. This square thing with the diagonal line across it is a coil. And you can see from pin 85 to 86 is the coil connection. Pin 30 to 87 is the switch connection. This is the control circuit. This is the power circuit. Every relay has two parts, the control circuit and the power circuit. Low amps, high amps. You can see, since every electronic device is drawn in its de-energized state, its resting state, you can see that this is what we call a normally open switch. See, it's open, no current flow. It's only when we energize this coil that this switch closes and allows current flow between 30 and 87. That's a normally open switch. And you can see it's rated at 200 amps. But we ain't, see how big these lugs are? We ain't using 200 amps to control it. We're using milliamps, maybe 1 amp at the most. So let us look. And we can see a variety of relays. But what I wanted to show you was, come on, not that one, not that one. That's a starter relay. You can see that the control uses a much smaller current than what it's controlling. This lug goes to the battery, and this lug goes to the starter motor itself. So when I energize 12 volts here, it's going to pull a big plunger down and connect this to this. That's how it works. It's kind of a different way of configuration. Let's see. There we go. These are the ice cube relays, and you can see here that these are fuses, and they're color coded. This is 10 amps, 10 amps. The red ones are 10 amps, the blue ones are 30 amps, and the yellow ones are 20 amps. ATO, ATC blade fuses. Often in a fuse block, you're going to see these relays. And these relays have options. There you go. This is what it looks like. This is the most commonly used relay in automotive. You can see it's got 5 pins. 85 to 86 is the coil. That's the control. Now, here's the part you need to understand. This is normally open, see the NO? This is normally open between 30 and 87. But look, this is a little more sophisticated than what I drew. Between 87A and 30, it's closed. Those are together. So a relay can be used to either complete a circuit or open it up. So if I wired this up the way we've wired up our relay, except I put the motor lead on 87A, the motor would run all the time until I energize this coil. This lever would come switch down, and then we would have an open here and the motor would stop. So either way you want to do it, 30 is normally closed with 87A, 30 is normally open with 87. If I energize the coil, both of those get reversed. That makes sense? You can watch the video if it doesn't make sense later, and if it takes a little slower. I mean, I don't want to go too fast, but there you go. There is a cutaway of an ice cube relay, and you can see the coil with very, very small wire. This little shelf pivots, and you can see a contact here and a contact here. When I create a magnetic field here, this shelf is going to pivot down and connect that contact point to this contact point. And here's the return spring right here to put it all back after I stop the flow of current. Yeah, I got that. This lesson I kind of got down, so I'm happy about that. Every once in a while. Oh, there it is. Okay, so there you go. And I already showed you all that. This is the video. Oh, that's not it. Is that engineering mindset?
This device
Yeah, it
is an
is.
essential.
That's the video you should watch, folks. How alternators work by the engineering mindset. I'm gonna take a picture of that, whatever. Engineering mindset does a bunch of good stuff. The other people, sometimes I'm nervous, but this is a great video because what it's going to do, it's also going to teach you 3-phase, which is a big deal. See, it's going to teach you 3-phase, which, Gabe, you should watch. Make that money, brother. Make that money, brother. If you don't have a retirement plan already in effect, you need to get one, because being old is no fun if you're broke or you're sick, right? Okay, so let's go back. Questions, comments, thoughts on that?
I was today, I just wired up a solenoid today. We were working on coolers. So I wired up a whole cooler, and the blower operates in the same way. There's a solenoid inside the blower. It's powered by the compressor up on the roof. You know, the flow of current goes, it's all the same application.
It is. Right?
Yeah.
Yeah.
I'm kind of being blown away right now, because then also like dealing with the contactors the same way, has a magnetic field, and they just open up, you know, we call them clackers because they clack, you know, and
yeah. Good. I'm so glad you're here, Gabe. I'm wondering where the hell you been. Okay, look.
you know, when classes started. My
I
bad.
sent you invites like 3 times a week. Okay, anyways, I'm glad you're here. So there's the coil. And it has continuity. Continuity means that I will have current flow in the presence of voltage, right? If there's enough voltage, or if the resistance is low enough, I will have current flow as long as I have continuity here. Now, didn't we talk about what determines the resistance of a conductor? Remind me, didn't we? Michelita, do you remember? Can't remember if it's this class. Yeah, there's 4 things that determine the resistance of a conductor. I don't want to repeat it if I did. 4 parts of every circuit. That's it. It's going to take less time just to teach it again. No. 5 elements of tune-up. Oh, no. Yes, I've given you all my secrets. All right. 4 things. This is gonna explain to you table 310.16 and the other one, table C, I guess this. 4 things determine resistance. Sorry, getting too fast. Of a conductor. And in the presence of voltage, whether it's 12 volts, 5 volts, or 240, 480 volts, what determines the current flow is going to be the resistance of the circuit. So let's check this out. 4 things determine the resistance of a conductor. Spell it right. Number 1, the material. You know, copper's a good conductor. Silver's a better conductor. Steel's okay. Aluminum's okay.
Isn't gold the best?
No, silver's a better conductor than gold, but silver will oxidize. It will tarnish. It will corrode. The advantage to gold is that it won't oxidize. It won't corrode. It's
Isn't
not the world's best conductor, but it won't oxidize, right? It doesn't need to be polished all the time because it doesn't tarnish like silver does. Silver, I mean, look at silver candlesticks. They turn black, right?
Well, usually they use the gold. Gold is mainly used like in motherboards, computer chips.
Right. Why? Because the least bit of corrosion will cause enough resistance to make these things not work correctly. I'm glad you asked. I actually knew the answer to a question. Yeah, it's for corrosion resistance.
Oh, okay.
Well, I mean, look what happens to copper when it gets a little bit wet. It turns green, right? It corrodes rapidly. So does aluminum. Well, steel rusts. Gold doesn't do that. All right, number 1 thing that determines the resistance of a conductor is material. And we're trying to answer how much resistance is there going to be in a coil. How much can we expect? Number 2 is going to be length. Now, every inch of conductor has resistance. So if you have a mile, it's going to have significant resistance. In fact, if you look up, well, it used to be 310.16b. I don't know what it is now, but it's pretty close. You'll see that resistance per foot, the longer it gets, the more resistance you're going to have. One of the calculations you have to make when you're sizing conductors is you have to figure out the length. All right, number 3, the diameter. The bigger the wire, the less resistance it's going to have. Just like trying to drink through a small straw takes a lot of suction. That's why In-N-Out gives you a big straw, so it's much easier, and you end up draining your drink really fast. Yeah, that's why you go to In-N-Out on a hot day, you always run out of your drink way quicker because they got a bigger straw. It's less resistance. That's why on 4th Street, they're replacing whatever drain pipe they had with like a 10-foot in diameter one. The bigger the pipe, the less resistance to flow there is. Same thing's true with the conductor. Number 4 is temperature. Oh, I drained my 3rd pen today. That's funny. All right, temperature. Everything expands when it gets hot. So the hotter it gets, the longer the conductor is going to be. Therefore, the more resistance it's going to have. Yeah. So what determines how much resistance there's going to be in a coil? The size of the wire. It's almost always going to be copper. So it's going to be primarily the diameter and the length. So how much should we expect? Well, I don't know. In a fuel injector, it's 16 ohms. In a pickup coil, it's, I don't know, 700 ohms. But I know one thing I better have is I better have continuity. So let's make sure we understand. The number 1 thing that kills every electromagnetic device is open. Sorry, it's an open. See that? There's no continuous path. Without a continuous path, we can have no current flow. Without a current flow, solenoid, relay, transformer, motor, generator, they're not going to work. Now, what causes this open? By heat.
I was gonna say that.
Yep. Now, there's two things there's two types of heat, right? One, heat caused by current. And that's very, very common. It starts to flow a little bit too much current, and eventually the copper, which is a soft material, just kind of melts and opens up. Now you've got no current flow. The second source of heat is ambient heat. And this is what you got to be careful of, because inside an engine compartment, it gets really hot. And that softens up the copper, right? So two types of heat caused by current and ambient heat. Let me ask you a question. Does that little strand of copper know which kind of heat is overheating it? No, it's all heat. It's all heat to the copper. So whether it's too much current, or whether it's too much ambient temperature, or whether it's a combination of both, which is what it usually is, this thing's going to open up. And when it opens up, party's over for that device. Most common cause. Because why? Because we tend to make these coils out of such small wire. Okay, now let's talk about that for a moment. Sorry, you got that?
Yeah.
All right. Ohm meter testing. Here's what we got to understand. This goes like this. I've got my beautiful ohm meter set on ohms. I've got red wire coming here. I've got black wire coming here. Now, Charles Reyna, is an ohm meter polarized? Does it matter whether we put black here, red here? Good, good. Ohm meter's not polarized. It's just like AC current or AC voltage. It's not polarized. So either way we do it, it's going to come up with the same answer, with an important caveat that I need to talk to you about in a moment. So what am I looking for when I'm testing a coil? Well, if I can look up the specifications, I'm going to look up the specifications. For instance, like on General Motors fuel injectors, they're going to say like 16 ohms plus or minus 1 ohm. That means as long as it's between 15 and 17, you're fine. What you're going to find out when you have a bad fuel injector is it's going to go 16, 16, 16, 10, 16, 16, 16. See the bad injector? The bad injector is the one that doesn't have a similar resistance to all the others, because it's a solenoid valve. Are two solenoids going to act the same if they have different resistances? No, because they're going to have different current flow. So one's going to open faster, one's going to open further, stay open longer. So in terms of fuel injectors, we need them all to be very, very close in terms of resistance value. The closer, the better. Almost always when an injector goes bad, it's going to go 16, 16, 16, 6, 16, 16. And that's the bad injector. You test resistance of injectors? Yeah, you just take off the little connector, and that gives you access to the coil. Easy. If we were at the freaking shop, I'd show you. Easy, easy, easy. You'd say, man, I know, now I know how to do it. Yeah, okay. But here's what I don't want to see. If this is, well, yeah, let me reverse this to make it easier. Uh-oh. And then this comes over here like this. It's got to open. Now I've got my ohm meter like this. This is the big conceptual mistake that most people make, and It has to be trained out of you. All right, I come over here with my negative lead. It don't matter, it's not polarized. Come over here with my positive lead. This has an open. Is it going to read 0 resistance?
Yes.
No, the opposite. Look, is there 0 resistance is there 0 resistance to me driving to Hawaii? No, there's infinite resistance to me driving to Hawaii because there's no path, right? This is the thing that you have to be trained out of, because we look at this and we say, well, there's 0 current flow, there's 0 resistance. Let's remember the relationship between current and resistance. If the current flow is low, then the resistance must be what? High, because they're in opposition. And if the current flow is high, then the resistance must be low. Okay, look, there can't be any current flow in this coil. Therefore, it must be because the resistance is too high. This is what we call infinite resistance, which is the technical term. Infinite, finite means count, in means you can't. Infinite means you can't count it. What it looks like on the meter is OL. And that means either out of limits, that means so much resistance that it can't even measure it, or over limits, which is basically telling you the same thing. Let me prove it to you. Here's my meter. Uh-oh. Here's my meter, and it's on ohms. These leads are currently not touching each other. What does the meter read? OL. Because the resistance is so high, the meter can't even read it. Now, if those leads touch, now you've got very low resistance. There's something wrong with these leads. You notice that, Chuck? It's reading 11 ohms. There's something wrong with it. Should read 0, right?
Yeah.
Yeah. Okay. If there's no continuity, if there's no continuous path between these leads, it's going to read OL. And that's the #1 technical mistake people make using meters. And it's going to screw you up bad because it's going to give you the opposite results of what you think. Yeah, so just remember, infinite resistance shows up as OL. It's just like, I mean, you could hold these leads 6 feet apart. It's going to give you the same reading. And that's what happens when a coil is bad. Typically, when I'm troubleshooting a solenoid or a relay or something like that, or anything that has a coil, what I'm going to do is I'm going to take my little ohm meter and I'm going to test the coil, right? Remove it from the circuit. Don't ever use an ohm meter on a powered circuit, that's for sure. Don't ever use an ohm meter on a powered circuit because it's got its own power source. I'm going to remove the device from the circuit and I'm going to test the coil and see if it's got resistance. Almost always, if it's got resistance, it's good. Because remember, most of the time, if it's bad, it's going to just show OL on the coil when it should be showing some resistance. Like I said, pickup coils, typically 200 to 700 ohms, but I've seen them 60, I've seen them 120. So don't use that as, you know, the number that it must be. Fuel injectors, 16 ohms. Now, let's think for a moment so I can get to the next point. If the fuel injector has 16 ohms and the pickup coil has 700 ohms, which one's going to flow more current? The fuel injector, because the resistance is lower, so the current flow is higher. Remember, resistance and current are always opposite. Yeah? You got that? Because I need to write down a safety warning. Never use an ohm meter on a powered circuit. Man, see, because I want a whole bunch of students here, primarily for the reason that, you know, you take your car to the shop because you need it fixed, you're probably going to know more electrical than the person you take it to. Never use ohm meter on a powered circuit. Yeah, it'll cause, battery explosions, meter explosions, burnt leads. Yeah, you don't want to do it. So I don't usually like to teach people ohm meter use, but we're on it right now, so that's where we go. Now you say, what about the continuity tester? See, this thing right here is a continuity tester. And you say, well, aren't we testing continuity? Yeah, we are, but there's things about the continuity tester that you need to know. Continuity tester looks like this. It's like continuously bigger curves. And it does test continuity. It tests it with a beep. So if I come down here to continuity tester and I go like this, you can hear that. And it does give you an ohms reading, 13, whatever. It makes a beep. So would that be a faster, easier way of testing coils? Yeah, but it's got one problem. And that problem is so huge that I usually don't use a continuity tester, to tell you the truth, unless I absolutely have to. Now I'll use continuity tester to test a wire or a switch, but in terms of testing coils, it's got a problem. And it's got a problem that's so large when it comes to testing coils that I don't think it's feasible. We found that the continuity tester will only beep up to 52 ohms, which seems weird, but this is independently verified. If you have more than 52 ohms of resistance, it won't beep even though you have a continuous path. Now, I think the number will show, but it won't beep anymore. As a result, if you're not careful, you'll say, there's no continuity in this coil. Let's go buy another one. And guess what? If it's got 200 ohms resistance, even if it's perfectly good and it's got continuity, this thing won't beep. And if you're using continuity tester only and not verifying it with an ohm meter, you're going to say this part needs to be replaced when it doesn't. And that's bad, because sometimes it's like, okay, well, so we can't get this part because the nearest one is in, Georgia. So we're going to have to call the customer and tell them we have to wait 2 days. And then you get the new part and it doesn't fix it. That makes you very unpopular. Or this is for you, Gabe. Or you come in and you're testing the windings on a 3-phase motor, something that costs thousands of dollars, and you're using continuity tester and it's got, 70 ohms of resistance. It's not going to beep. And then you tell your boss, yeah, this motor's bad. You need to get another one. Thousands of dollars shipped overnight. So thousands of dollars worth of shipping. And then you install it and it doesn't fix it. Make you very unpopular. Make your boss very unpopular with the person he's working for too. So
that just happened when I replaced the starter relay on my work truck. So we didn't test it. We just replaced it thinking that was the issue, and it wasn't. So that one that we took out was still good. And now that you're teaching this right now, all we should have done was just test it with the ohms, and we would have known.
Yep. Yeah. Well, that's why I say everybody should be here, but they ain't. So sucks to be broke, I suppose. So that's what I wanted to teach about the continuity tester. Now, usually I don't like to teach students ohms because they start going ohm crazy and testing a bunch of stuff. The ohm setting and the continuity test, which is a type of ohm setting, are potentially dangerous. You need to have some, mileage under your feet before you start using ohm testing, other than just like basic stuff. But if you put the ohm meter across a battery, one of those batteries would blow up and it wouldn't be good. Things would start getting really hot. So that's why ohm meter testing, you gotta kind of chill on. Now I don't really have anything that has resistance here to test, other than, well, yeah, sure I can. You got that? Let's go to ohms. Now there's a problem with testing, well, something's in a circuit. I'll just go from here to here. Remember, when you're using a meter, these little rings are for you to keep your fingers behind. I see people getting in the habit of doing this. Then they test freaking house voltage and they get nailed. This is a sophisticated piece of equipment.
Yeah.
You need to respect it. Keep your hands behind these little rings. So I come in here and I test this resistor. And it says,
1.1.
it says 11 ohms, 11.2 ohms. Now, let me show you something, guys and gals. Look, I'm coming in here and I got, oh, it's easy to read this way. 1.198, see the small k in front of the ohms? 1.198 kilo ohms, that's 1198 ohms, because kilo means 1,000. Now, if you're not getting a stable reading, that means you need to reposition your leads or figure out why. If the reading keeps bouncing around, that tells you that you don't have a good connection. Now, if it's bouncing around from 1.93 to 1.92, I'm not concerned about that. It's when it goes from 3 to 15 to 26 to 4. Yeah, then you got a problem. Let me test another one. 1.2. I must be good at this. I bet you that's supposed to be the same value. 1.2 kilo ohms. It's 1,200 ohms. Now you'll notice that I'm testing the resistor in the circuit. Technically, that's asking for it. Because, let me show you why. Here's your resistor. But what you don't know, and this happens a lot on relays and solenoids, what you don't know is that somebody's come in here and connected a diode. Do you know what for, Chuck?
Yeah, keep the car going in one direction.
Well, that's what the diode does, but do you know why they put it across a coil winding? It's for spike suppression, because every time it opens or closes, there's going to be a big old voltage spike. If the resistance remains the same and the voltage goes up, so the current will too. And what they're trying to do is they're trying to protect the coil. So they put this thing called a diode across it to keep that big old spike from happening every time you open and close, or activate the coil, I should say. Well, here's the thing. Diode looks like this. We talked about the diode in this class?
No.
Okay. Chuck, I'm going to draw you the best diode you ever saw drawn. And it looks like this. It's going to be black, usually, with a silver stripe. And it's going to have a part number on it somewhere. That's called a diode. And that's an electrical one-way valve. I guess that's a form of control. Want to see a diode? See these black things right there? Oh, shoot. I need to get a better camera. There. Here, here, and here. See those things that are black and silver?
Yes.
Look like my bitchin' drawing. Now this is a good camera. And they got part numbers on them that are going to tell you how they act. Okay. Those are resistors down there, incidentally. That's a great camera right there. And I bought it for myself. Okay.
You're not gonna make us count the stripes on the resistor to know what it is, are you?
No. A diode is going to have high resistance in one direction. Sorry. And low resistance in the other.
That's how LEDs work, right?
Yep. LED stands for light emitting
Diode.
diode. Yep. Good. Good. Okay, well, we have one-way valves in our heart, right? That makes it easy to push fluid out, but it makes it so it can't come back. In fact, when those valves go bad, that's why you need a pacemaker. I actually saw it on my dad's heart, and when the blood goes backwards into the heart, you can see it thermally on thermal imaging. It's really interesting to watch. He didn't enjoy it, but I did. That was a joke. So here's the problem. A diode has high resistance in one direction and it has low resistance in the other. If there's a diode in the circuit that you don't know about, when you test resistance this way, it's going to have a different value than if you test it this way. Right? Because how the ohm meter works is it puts a certain voltage on this lead, then it measures the voltage on this lead, and it calculates from the voltage drop how much resistance there is between the two. So it's actually using a battery to put voltage on this lead. So it's creating DC current if you make a circuit. It's going to have a different resistance in this direction than it has in this direction, which is why when I'm doing an ohm meter test, I don't want to get caught by this. I don't want to get tricked by this. So before I pronounce this a bad part, hopefully I remember and don't get too excited, I'm going to reverse my leads and make sure that there's not a diode in there that's going to fool me. And as I say, in solenoids and relays and stuff like that, you're often going to see that diode, and it's there for spike suppression. Just something to think about. That's why you're not supposed to test resistors in a circuit. And when I showed you testing these resistors in a circuit, you know, if they got a diode, I mean, who knows what the value is? Who knows what the rest of the circuit is? They could be in parallel with 8 other resistors, which would change the resistance. So be careful on that. But the big takeaway I want you to have on this is don't trust the continuity tester, because if it goes over 52 ohms, it's not going to report. And then, you know, the big thing we have to do, okay, what's more important, that we do the right thing, that we don't do the wrong thing? Both, really. So it's important that we don't pronounce good parts bad. Well, it's important we don't pronounce bad parts good, too. Yeah, woe to you, heck quack. All right, so diodes all over the place, especially in like the alternator, big old bunch of diodes. All right, questions, comments, thoughts on that? What do we do for a stronger relay? Same thing we do for a stronger solenoid. Increase the current flow, increase the number of windings. Now, as I said, relays are being replaced with solid state devices. Solid state meaning that there's no moving parts. And that solid state device is called, how will I draw it, Chuck, like this? And this comes out like that. Okay. Then you got
Yeah.
three little suckers that come out like this.
Transistor.
Yep. This is power transistor, and what it's doing is it's replacing relays. We don't have real high current capability economically now, and everything's set up for relays. And after all, what do we call that? You know, 4826B, whatever part number. And this right here is a heat sink because it's going to get hot. That's called a transistor. Think of programmable logic controllers. They took the relays out and they replaced them with transistors. That's why they're so freaking expensive. Do I have a transistor to show you? No, I got a bunch of integrated circuits. That's got a bunch of transistors in it, but I don't have a transistor on this board to show you. unfortunately. Hey, let me ask you a question. Here's a bunch of really thin wires, and here's a bunch of really thick wires. Which one carries more current?
Big ones.
Yeah. Can we make some judgments about what's going on just looking at the size of conductors? Sure, because the size of conductors is always going to be proportional. Sorry. The size of the conductors is always going to be proportional to the amount of current. So these little circuits are information circuits, milliamps if that. These are the leads that go to the big relays that I showed you that roll the window up and down. These are the ones that go straight to the motor, so they got to be big. So the good thing is if we understand the principle of ampacity, we understand a little bit about wiring and electricity, we can tell how much current they're expecting to have in the circuit just by looking at the size of the wire, which is helpful and good, you know. It tells us that a fuel pump draws a lot of current. It's got a big wire going to it. It tells us that the starter motor draws more current than anything else in the car because it's got the biggest wire in the car going to it. It tells us that a radio doesn't draw that much current because the wire is kind of small. Now, when we look at like stereo installations, aftermarket stereo installations, if somebody's claiming 1200 watts on that stereo, it better have a huge freaking cable going to it, because if it doesn't, or a speaker wire, if the wire is not that big, you're not going to get that much boom out of it. That's a transistor, and a transistor is a member of the solid state family, and they call it solid state because it's got no moving parts. Relays will wear out. That contactor, every time the contactor makes contact and then releases, there's going to be an arc. And eventually it will pit up that contactor just like breaker points in the old style distributors. Yeah. In fact, back when I was Chuck's age, they used to have these things called external regulators on the alternators, and they used to actually have a relay there to control the amount of output out of the charging system. Now that's been replaced by transistors, and you know, now the voltage regulators like this little, looks like a freaking ice cube size thing, or one of the pieces of a Hershey bar. Pieces of Hershey bar, not the whole thing. I'm looking forward to seeing more and more transistors. If, for instance, we want to have solenoid valves for our intake and exhaust valves, which they would love. You know why they can't do that yet is because the things would overheat. They have to generate so much force, and they're activating so much. I mean, at 6,000 RPM, they're activating 100 times a second. No, 100 times a minute. Okay, let me slow down. 6,000 RPM. They're activating 100 times a minute. 10 times a second. Yeah, 10 times a second. Opening a big old, 2-inch valve 10 times a second. That's taking tons of power. That's why they haven't replaced. That's the only reason. Because if we could replace the intake and exhaust valves with solenoid valves, that means no more cams. No more cams means we can open up valves anytime we want. Means we could have individual valve timing for each cylinder. Means no more cams, no more timing chains. It takes a lot of power to turn a cam, but we can't get these solenoid valves to keep from overheating because they're just doing so much work. But progress in solenoids, progress in materials, progress in transistors instead of relays. You'd never get a relay to do 10 times a second, I don't think. I could be wrong, but it wouldn't do it all day long. I know that much. Besides, they're running stuff like that on like 600 volts. They're running on big voltage like the injectors on diesel electronic fuel injection. They're running big voltage on that. We got to talk about transformers at some point, but it won't be today. So we're going to hum, right? We're going to hum, and we're going to bust through electromagnetism next week. What do we got left? We've got, I think we're done on relays. We've got motors and generators and transformers. I'm sorry, motors, generators, and transformers. So we'll bust through that quick. Folks, we got a budget of 20 weeks. Now this is the 3rd week, so we really got a budget of 17 weeks. We got to not only finish our electrician fundamentals, but then start applying it to everything on the car in 17 weeks. So let me know if I'm going too fast, and don't think of it as an interruption, because after all, that's, you know, you're the student. But we do have to have a workmanlike attitude, shall we say, on getting through this material. Engineering Mindset is a great resource, If you wanted, you could watch the Scott Brown video. You'd find it very helpful, because what he does is he ends up showing you the waveform of a fuel pump in operation, which is awesome. I mean, the stuff he's doing, I didn't like the resolution on one of those videos, but the one that had, but maybe that's my computer. I don't think so. But he said that video's actually a year old. He just finally put it up a couple of days ago. So our Kelly puts out new material, and so does Scott Brown. Let that be the similarity. Questions, comments, thoughts on that? Let me ask you a question. This is the starter relay, and this is the headlight relay. They both have a part number 2178436. 2178436. Both of these relays have the same part number. This one's for the starter, this one's for the headlights. My question to you is, if my starter's not working and I want to test to see if it's the relay, can I pull this relay out and put it in that socket?
Sure you
No.
can.
Absolutely you can. It's got the same part number. Now, if it's got a different part number, don't do it. Because, you know, different part numbers are going to have different trigger coil current, different power current. But if it's got the same part number, swap it. Just make sure this one works first, right? Turn on your headlights, make sure your headlights come on. Then I'd swap it. I would swap it all day long. You know why? Because you could test it with a meter, and you could test it with fancy relay testing tools, but this is quick and it's righteous because it's the same freaking relay. There's a bunch. What?
I got a Dodge Charger started one time.
Right.
I pulled the wiper blade relay out, stuck it into the starter relay. Car started up.
Yep. Down the road you go. And I'll bet you didn't have wipers for 3 or 4 years after that. We all get busy, right? All right, Mr. Burks, what are you going to do about your car problem?
Jack it up again tomorrow.
Yeah.
And let some brake fluid out and
I
compress
have a question. One more
Yes.
question. On those rotors, are they the hat style or were they you have to remove the wheel bearings?
had to remove the wheel bearings.
So
Oh,
when you put the new rotors in, you had to put new bearings and races in?
Yes,
Did you make sure that they're fully seated?
yes.
yeah.
Okay.
How do you know? How do you know they're fully seated?
How?
How do you know?
Well, the wheel wasn't wobbling.
Yeah. Yeah, but that doesn't tell you they're fully seated.
That's right. That's
Here's how
right.
you tell. Okay, were the races already installed, or did you install them?
It was already.
Okay, that's better. All right. So what else? There's a step. Okay, when you put the rotor in and then you put the caliper mounting bracket on, is the rotor centered in the caliper mounting bracket?
Yes.
Okay. Now, is this happening on both sides or just one side?
Well, I only did the right side and touched the left side.
Oh, okay. All right. Well, a lot of times you can compare the two sides and see if you can see anything that's amiss. But I'll tell you, I'm not a big believer in that blue Loctite on those caliper mounting bolts, and I think you might have a problem getting them off now, because those are supposed to be torqued to like what, 130 foot-pounds?
166.
Geez, if they ain't coming off, why would you Loctite those? According to me, I mean, They ain't coming off. 166 foot-pounds, that ain't coming loose. Okay. Well, let me know.
Okay.
I apologize for not being really quick on my response, but
That's okay.
yeah, we'll do our best. We'll do our best. Now you didn't put the brake pads in backwards.
No, I
Uh,
hope not. I think they only go on one way.
Well, we got a couple of minutes. How much have you bled brakes before?
That was the first time.
Oh shoot. How'd you do it?
I had someone inside the vehicle pumping while I opened the valve back and forth. I tried the one person at first, but it was taking too long.
Yeah, it takes much more longer.
Yeah,
Okay,
so I
now,
had,
when you first put the caliper on with the brake pads in it, there was space between the pads and the rotor, right?
correct.
Okay. And the first time you apply the brakes, the pedal goes way down and it pushes the piston out. And now
Well, I didn't get that far. Once I put the pads into the bracket, then I put the caliper on top of that. That's when all of this clearance went away. Before I put the caliper on, I had space. You know how the bracket goes over the rotor?
Yeah.
Then I put the pads inside the bracket. Then when I got my rotor to put the rotor on, that's when the pad on the brakes compacted onto the rotor, and the caliper. There was no space between anything. It was just rubbing.
Can I interject for a second?
Please.
Uh-huh.
Well, I'm assuming that's the driver's side you're working on, right?
No, the passengers.
Okay, well, the driver's side's intact right now?
Yes.
Well, just for shits and giggles, why don't you pull that one rotor off, stick it on the driver's side, see if there's any difference.
Well, you still
Okay.
got the old rotor, right?
Yes.
But you could use that, or you could use the other rotor just to see, because I'm still kind of skeptical on those bearing races, you know.
Yeah, but that,
if the old rotor, put it on, put it back on. If not, use the other side.
yeah, but Chuck, I don't think the caliper will fit over the rotor, which wouldn't be a bearing issue.
Well, I'm thinking if the bearings weren't seated, that rotor could be out. You know what I mean?
Right. So which we could find out by seeing if the caliper will fit on the rotor when it's
Right.
outside the mounting bracket.
Right. By taking the old rotor or taking the other side off with those
Okay.
bearings and races and stick them on there just to see if that caliper will slip on with the new pads.
Yeah, but he said that the rotor is centered in the caliper mounting bracket, which
He
would,
said he lost the gap. I'm assuming he lost the gap
Yeah.
from, in and out.
now
So
what I would put the pads in the caliper and see if they fit over the rotor as is. See, because what Chuck's saying is that the rotor isn't centered in the caliper, and that's
Right.
what's causing your clearance issues. So I
Okay.
would take the caliper out of the bracket and see if it'll fit over the rotor, and that's your issue.
Oh, okay. Okay.
Yeah.
Okay, I'll try that tomorrow night.
Well, Chuck's available between midnight and 3 in the morning. So
No, I think I'd
Where's
be
my
too tired by then.
if he doesn't pick up, just keep calling.
Okay.
All right, guys. Did you learn anything? Okay. Where's Rudy? Where's Jerry? This is a huge mistake. Hopefully Rudy's doing well. He was having some kind of complications with this freaking house, of course. So, welcome to the joys of home ownership, right? All right. Well, Thursday. Okay, I'm gonna tell you the same thing I told the students this morning. Martin Luther King said, and I taught all my kids this. Martin Luther King said, "I have a dream that someday my 4 children will grow up in a country where they'll be judged by their content of not by the color of their skin, but by the content of the character." Turns out people have decided that's racist now to do that. So what I'm gonna suggest to you is we gotta quit expressing any type of political leaning or any type of controversial opinion. We gotta get our no pictures. You know what I told my daughter, Gabe Alvarado? You know what? I have 5 daughters. You know what I told them? No pictures, no videos. No pictures, no videos. All right, we got to back up off of social media because people are getting fired for stuff they said 20 years ago. And the worst part is, you know, the stuff I say, it was common sense 40 years ago. Now I say it and people are like, where'd you come up with this radical view? Well, hopefully 40 years from now, well, I won't be here, but hopefully 20 years from now, it'll be common sense again and I'll be a genius. Anyway, I'm going to suggest, especially if you have children, you need to get them to back off the freaking internet. Because, you know, plus, I mean, I'm getting emails about how to stop a barking dog. It's like, how do they know I have a dog? Right? How do they know that my dog's barking bothers me? It's like, I think all your internet traffic's being stored, and they may not be sifting through it now, but they'll be sifting through it soon. When they get the computing power, it'll be easy. I mean, I went to Kaiser Hospital, and they take your picture now. You don't think they're going to start doing that on every government building? You got to get your picture taken. So anyway, my point was, let's back up off. You know, social media is fun. Oh, look how drunk he was on Saturday. No. We don't want our young people to wreck their lives for some innocent fun when they were 15. They thought was innocent, but no, other people won't think so 20 years from now. So that's my theory on that. I sure appreciate it, folks. I got to make sure that wife has what she needs to go to work. So I appreciate it. Thanks so much.
Right.
Let me know. And like I said, Michelle, if you could try Electude, that'd be awesome. If you're going to be here, see, I was waiting for Gabe to show up, so now I can give him some Electude. And that will give you more electrical training that you can access anytime you want. It's car-based, but it still applies to everything. So have a great week, guys. I will see you on Thursday, yeah? 6 o'clock.
All right.
Can't wait. Thanks so much.
All right.
Always the best cap to my day. Sure appreciate it. Good night.
All right.